Thank you for the introduction. My name is Ghanesh Narasimhan. I'm a postdoc at the University of Minnesota. Today, I will talk about an a priori LUS study on turbulent curvilinear model for quantifying wave-induced airflow perturbations. The motivation behind the study is to characterize the influence of waves on marine atmospheric boundary layer flows. Waves affect ABL in two ways. First, they excite airflow disturbances, and they also induce form drag on the flow within the wave boundary layer region. Both processes affect the momentum and energy transfer between wind and wave fields. Accurate modeling of these effects allows us to parameterize the influence of waves in weather models and wake models for offshore wind turbines. In this work, we study wind-wave interaction by performing large eddy simulations of wind over swell. This is a phase-resolved LES where we resolve the wave phase information using a boundary-fitted grid as shown in the top left video. As a result, at each time step, we map the governing Navier-Stokes equations to a curvilinear coordinate system that follows the wave progression. The code uses pseudospectral discretization in horizontal directions and second-order central finite difference along vertical direction. This is also a wall-resolved LES where the viscous sublayer region is resolved corresponding to a friction Reynolds number of 1000. The domain details and other simulation parameters are listed in this table. The wave steepness is set to 0.1 and the wave age is varied between -25 to +25, where the positive and negative values represent wind following wave and wind opposing wave scenarios respectively. Once these simulations reach a steady state, we perform triple decomposition analysis. Here, we decompose an instantaneous field into a mean component, wave-induced component, and the turbulent fluctuation component. The mean and wave-induced components are obtained through a phase averaging operation where we average the data in time by walking along the wave characteristics. In this slide, we show the wave-induced pressure on the left-hand side and wave-induced vertical velocity fluctuations on the right-hand side for wave ages -15, -2, +2, and +15. The waves create alternating patterns of pressure whose vertical gradients generate forces that drive the upward or downward fluid motion related to the wave surface. And this results in the alternating pattern of the vertical velocity perturbations as shown on the right. These perturbations are stronger under high wave age and wind opposing wave conditions as seen from -15 wave age case. The strength of these airflow disturbances decreases as we move towards wind following wave conditions. Now, can we predict these varied characteristics of wave-induced disturbances across different wave age conditions? The answer is yes, we can predict them. In order to make these predictions, we first decompose the wave-induced fields into fundamental Fourier modes by neglecting higher harmonics. The wave number of the fundamental mode is determined by the wave number of the swell. We then derive the model to predict the Fourier coefficients of the wave-induced fluctuations. Previously, Cao et al. Of 2020 developed a model called the viscous curvilinear model to predict the airflow disturbances. In this study, the authors derived governing equations for wave-induced motions. We start with Navier-Stokes equations in wave following curvilinear coordinate system. We then phase average this equation and obtain phase average Navier-Stokes equations. This phase averaging operation gives rise to the nonlinear turbulent stress term. We then horizontally average this equation to obtain the governing equations for mean flow. This horizontal averaging operation gives rise to the nonlinear wave-induced stress term. Then, upon subtracting the mean equations from the phase averaged equations, we obtain the governing equations for the wave-induced motions. Next, we apply the Fourier ansatz and simplify the wave-induced governing equation following the same spirit as deriving the Orr-Sommerfeld equation. We linearize the equations by dropping the nonlinear wave-induced stress and turbulent stress terms. We further simplify the equation by eliminating the wave-induced streamwise velocity and pressure quantities. The resulting equation is an ordinary differential equation for Fourier coefficient of wave-induced vertical velocity or W hat. Quite interestingly, the linear operator on the left-hand side is similar to the Orr-Sommerfeld operator. However, unlike the homogeneous Orr-Sommerfeld equation, This ODE is non-homogeneous due to the presence of forcing term caused by the wave elevation. Once we solve for W hat from this equation, we can then obtain the Fourier modes of wave-induced streamwise velocity U hat and pressure P hat from the continuity and vertical momentum equations respectively. The plot on the top right demonstrates good agreement between LES and model predictions for vertical profile of W hat for a wave age of -14. Overall, the key takeaways from this slide are: the viscous curvilinear model is a linearized model for predicting the Fourier modes of the wave-induced motions. The model predictions are in good agreement with LES under high wave age scenario. The authors also highlighted that for low wave age cases, the turbulent stress terms become important and they should be included for making better predictions. Now, in this study, we extend the viscous curvilinear model by retaining turbulent stress terms while still neglecting the wave-induced stress terms. The terms marked in blue are the turbulent stress terms. We call the resulting equations the turbulent curvilinear model. I would like to emphasize that in the current work, we are focusing on a priori LES study. This means we are solving the model equations by directly utilizing the mean velocity and Fourier modes of turbulent shear stress components from LES. Now let us look at the results for wave-induced vertical velocity. First, we show the Fourier modes of the real part of W hat. Each box represents different wave age scenario as denoted by the title above each plot. The markers are results from LES. The blue line represents model predictions from viscous model, while the dashed red line are predictions from the turbulent model. For low wave age cases, that is C by U star -2, 0 and 2, we can see that the predictions from the turbulent model are in better agreement with LES than the viscous model predictions. Including turbulent stress also improves predictions for high wave age and wind following wave cases. On the right hand side, the predictions for the imaginary part of W hat are quite similar between both the models. Overall, this shows that turbulent curvilinear model performs better compared to the viscous model across all wave age scenarios. Similar conclusions can be derived for wave-induced streamwise velocity. The turbulent curvilinear model gives improved predictions compared to the viscous model across all wave ages. The same conclusion applies to model predictions of wave-induced pressure as well. The turbulent model gives improved predictions relative to the viscous model, although slight deviations exist for certain wave age cases. In the motivation slide, we discussed that waves induce form drag on the flow. The form drag is induced by the enhanced pressure distribution on the wave surface. The plots in this slide show the pressure distribution on the wave surface from LES and corresponding model predictions. The turbulent curvilinear model predicts the right pressure distribution across all wave age conditions. The difference is strikingly visible for wave age equal to 15 case. Although for the rest of the cases, the predictions from both the models look similar, evaluating the form drag by integrating the pressure over a wavelength reveals that the predictions from the turbulent model, denoted by the red markers, are better compared to the viscous model, represented by the blue markers, as they lie closer to the LES results, shown by the black markers. In conclusion, we saw that swells excite airflow disturbances, and we were able to visualize and understand its properties through triple decomposition analysis. We derived turbulent curvilinear model equations by extending the viscous model to include turbulent stress terms. A priori tests reveal that turbulent curvilinear model gives improved predictions of wave-induced fluctuations and form drag. The future scope of this work will focus on modeling the turbulent stress components without relying on LES data and evaluate the model predictions in a self-consistent manner. Thank you.